Alright, hello everyone. Welcome back. In this section, we are going to explore two examples of applications of matrices. Alright, let's look at the first one. Alright, now the matrix M is defined as a 3 by 3 square matrix given as such, where the restriction imposed on M would be M cannot be 0 or 1 or 2. Right? Now find a matrix P and a diagonal matrix D such that M is equal to the diagonalization, sorry, such that M is equal to the diagonalizations equation given as PDP inverse. All right. Okay. Now, how are we going to obtain the um, model matrix P and then the diagonal matrix D, right? Now, just to recap, diagonal matrix basically is a matrix that consists of all the eigenvalues arranged diagonally, right? Whereby the matrix P is a matrix that consists of all the eigenvectors corresponds to the eigenvalues obtained from the matrix itself, right? All right, let's take a look at how to work out each one of these. The starting point would be to obtain the eigenvalues. To obtain the eigenvalues, we always start from the definitions, which is ME equal to lambda E, where the lambda is known as the eigenvalues, and then whereby the E would be the eigenvector, right? So I hope that is clear. By definition, this is the equations that we are going to use to obtain the eigenvalues. Right? Okay, let's take a look at how to work this out. That will be typically ME. If we rearrange this, it will be the same as I lambda E equal to 0. And then that is the same as M. Okay. Now, for these characteristic equations, we know that one of the trivial solutions for eigenvectors is basically this is one of the trivial solution, which is 0, 0, 0. Right. Now we are more interested in a non-trivial solution. So in order to get the non-trivial solutions for eigenvectors, we have to solve this determinant equation. Right. Now, these determinant equations is also known as characteristic equations for the transformation matrix. Right. So I'm going to start off with this. That will be 2. Okay, we're going to subtract off this, which is lambda. Okay, and then we are interested to obtain the determinant for this. Okay, which is 0, 0, 0 to be precise here. Okay, now all we need to do is just rearrange this properly. So we have lambda 1, 0, m minus lambda 0 again, and then lastly 1 minus lambda. Oops, sorry, I think I write down the wrong symbol for this. Supposed to be 0, sorry. This one is also 0. I think I confused between the other one. Okay, 0. Now by solving this determinant, we will have, okay, I'm going to write down over here. We will have 2 minus lambda equal to 0. Therefore, all the eigenvalues, lambda, will be given by 1. It could be 1, it could be 2, or it could be m here, where m should not be 0, should not be 1 also, and then should not be 2 also, since we have already obtained two of these eigenvalues to be 1 or 2. So therefore the m should not be 1 or 2. You need to have, usually for a square matrix 3 by 3, we should expect to have 3 eigenvalues, right? And then those 3 eigenvalues are unique eigenvalues. There should not be any redundancy between the values here, right? And then lambda should not be 0 either. If lambda is 0, we indirectly obtain our trivial solution, which is eigenvector equal to 0 here. Okay, right. Now, that is our first part. I hope you are clear how to obtain this. And then, what is the use of this then? All right, now I'm going to summarize that. Once we have obtained the eigenvalues, therefore, we can conclude the diagonal matrix. And then, as I mentioned just now, diagonal matrix is just a matrix that store all the eigenvalues in a diagonal format. So therefore, D can be written as, if you arrange it in this manner here, or in this order, it would be this. Right. Now that will be your diagonal matrix that store all the eigenvalues in the diagonal form. So this is diagonal. Now we have successfully obtained the diagonal matrix here. Okay, so I hope that is clear. Now next, I'm going to move on to evaluate each one of the eigenvectors corresponding to lambda equal to 1, 2, and m. All right, stay tuned. All right, now I just copy down the diagonal matrix that we have obtained here. Now this diagonal matrix would give us all the informations regarding the eigenvalues here. All right. Now we're going to evaluate the corresponding eigenvectors that corresponds to lambda equal to 1, lambda equal to 2, and lambda equal to m. Okay, now I'm going to start off for lambda equal to 1. Okay, now we know that it satisfies this equation, right, for the definitions of eigenvector, eigenvalues. Okay, now from here, we're going to rearrange like what we did before. So indirectly, we will have like this 1, 0, and then multiplied by e, which is equal to 0, 0, 0 here. Okay, now at this point we are not using determinant because we have already obtained the eigenvalues using determinant. So here our intention is to solve for the sets of values for eigenvectors here, right? So all we need to do is just simplify this. We will have 1, that's m minus 1, 7, 0, 0, 0. Okay, And then we know that all eigenvectors can be represented as it can be represented as ABC. It doesn't matter. Okay. Okay, this is how it look like. And then we can convert this into Cartesian form. There are many ways to obtain the eigenvectors, but the one that is more comfortable to me would be to convert this back to Cartesian form. So in the Cartesian form, we have um, x plus my plus z equal to 0. That's our first one. And then second one will be m minus 1 y plus 7z is equal to 0. Now that will be our second system of linear equation. Okay. Now the only thing we don't have is we don't have the third linear equations because there can be many possible solutions for the z's. Now, because of that, we will let z be, in this case, because there are many solutions for z, therefore we are going to let z equal to t, for instance, where the t are all real numbers. Okay, now knowing that z is equal to t, we can obtain the y from the second equation here. Therefore, from here we can write down y is basically negative 1 over 7. Negative 1 over 7. Is it negative 1 over 7? Oops, sorry. Copy wrongly. Just let me correct that. So therefore, y is actually negative 7t because we let z equal to t. So therefore, negative 7t divided by m minus 1. Okay. Now that will be our y in this case. Okay. And then from here onwards, we can also solve for x here. Okay, so let me see what do we have here. Let me see here. X will be um, tougher to solve here. So I'll write down from there our x we can obtain negative t, and then we're going to subtract off with my. So that will be 7m over m minus 1 t. And then that can be simplified into, okay, in this case, let me see, into negative m, that will be 6m, okay, 6m plus 1 over m minus 1 multiplied by t here. And therefore, we have already obtained our xyz. Then from here, we can conclude that our first eigenvalue, first eigenvectors corresponding to eigenvalues of lambda equal to 1 as, I'll label this as E1, is actually equal to x1, y1, z1. So those unique values are, we have x equal to 6m plus 1 over m minus 1. And then y would be negative 7 over m minus 1. And then finally, that will be 1 t. Okay, t in this case. You can leave it in this form, or sometimes you might like to leave it in this form then, since most of them share the m minus 1. So you can actually take out m minus 1 because it's a constant. Therefore, there will be 6m plus 1, negative 7, and then this one will be m minus 1. Therefore, you can simplify the eigenvectors as, so sometimes you can write your eigenvectors as, sometimes they write in this form as 6m plus 1, negative 7, m minus 1. Okay. Doesn't matter actually. You can leave your eigenvectors in this form, or without the constant there. All right. Okay, now that will be our first um, eigenvectors corresponds to lambda equal to 1. Okay, now stay tuned. I'm going to work out the eigenvectors that correspond to lambda equal to 2. All right, now we're going to evaluate the eigenvectors corresponding to the eigenvalues lambda equal to 2. Okay, now the structure is more or less the same. The only difference is for the lambda equal to 2, this value will be 2, 2, 2. Right? And then we're going to perform the same procedure here. That would yield m 1, 0, m minus 2, and then 7, 0, 0, negative 1. Okay, so E equal to, all right. Now, as usual, we're going to solve for the E in this case, right? Now, for this is rather easier because we notice that the Z, okay, if we represent the E, okay, maybe I change the form a bit. If we represent the E in term of X, Y, Z, and then we're going to convert this back into its Cartesian form, uh, that would yield the first one, it would yield Z equals 0 as our first solution. Okay, now because Z is equal to 0, okay, now the second equations that we can obtain will be, okay, just let me write it down here, m minus 2 y. Okay, so that is y plus 7, oops, plus 7z is equal to 0. Now because z is actually equal to 0, therefore indirectly the y must be equal to 0. Okay, and then they go for the last equation also, but we have no informations about x. So here we can just say that let, let x equal to t, where it could be any real numbers here. Therefore, therefore in this case we can conclude, okay, from here we can conclude the second eigenvectors corresponding to lambda equal to 2 as, okay, now which is actually x, y, z, x2, y2, and z2. That is the same as our x2 is a t, the rest are 0, 0, or you can write down as this. Now therefore our second eigenvectors can be written as 1, 0, 0 here. Alright, so I hope that is clear. And then lastly, we're going to work out the eigenvectors corresponding to eigenvalue lambda equal to m. For the last eigenvectors, the structure is exactly the same, except that now the lambda is equal to m here. All we need to do is carry out the same procedure. Now we will have 2 minus m, m, and 1. Now here it will be 0, 0, 7. And then next we have 0, 0, 1 minus m. Okay, the eigenvectors here, I can represent it as x, y, z also. Okay, now from here is it's quite obvious that the z is actually equal to 0. Okay, and then the first equations that we can get from here would be 2 minus m x plus my plus z is equal to 0. Okay, now this equation is obtained from the first row here. Okay, now we know that z is equal to 0. Therefore, what is left is 2 minus m x plus my equals 0 there. Alright, okay. Now up to this point, you can let anything you like. So take for instance, from my point of view, I will let my y equal to t, where the t are all real numbers. Because y is equal to t here, therefore you can conclude that your x must be equal to negative mt divided by 2 minus m. Okay, now that is your x. And then finally, we can conclude that our last eigenvectors can be written as, I can rewrite this as, okay, let me take it out as in this form, m over 2 minus m, that's x, and then my y is equal to 1, and then my z is equal to a 0 there. Okay, or you could actually simplify in such a way that it could be something like this. Okay, I can write it down as negative m. This part will be 2 minus m, and then lastly it will be 0. Okay, now that concludes our last eigenvectors, which is negative m, 2 minus m, and then lastly we have a 0 there. Okay, right now I'm quite happy with all the result. I'm going to conclude, and then I'll provide solutions to this question here. Okay, now let me erase everything at this point. Okay, let me get a larger eraser here. Okay, so therefore we can conclude that our diagonal matrix, I just rewrite this one more time, which is given by D as 1 0 0 0 2 0 0 0 m. Okay, and then our model matrix, the matrix that represent or encapsulate all the eigenvectors, model matrix, which is given by P. Okay, now this one here is corresponding to the eigenvalues of 1, so I will write this one down first. Plus 1, negative 7. Okay, then the second one will be 1 0 0, and then lastly okay, now using these two solutions, we would be able to obtain the transformation matrix M by using these diagonalizations equations here. Right, now I hope that this sections is clear. Do drop a comment in case I make any mistake in my calculations there. All right, so stay tuned. We still have one more matrix questions that we're going to solve shortly. All right, this is our second and the last transformation matrix uh, question. Okay, now we are given a 2 by 2 square matrix that represents transformations P. Now we need to describe fully the transformation P based on the structure of the matrix. Now that's our first question. Now once we have done that, transformation Q is a stretch parallel to the y-axis with a scale factor of 4. Now, under this question here, we need to find the matrix that represent transformations Q using all the informations given. And then the third questions, transformation T is combinations of transformations P and Q. The order would be, we're going to start from transformation P followed by transformation Q. Now we need to find the combinations of this matrix that represent T. And then finally, using these transformations, matrix T, we are going to obtain the image for that unit square area that undergo the transformation matrix T. So we are going to study the relationship between the original unit square and the image under the transformations matrix T. All right, let's get started with this. All right, first section first. All right, we need to describe fully the transformation matrix P, and then what does the structure of the matrix actually inform us about this transformation. Okay, now let me show you the final result or the effect of this transformation if we are interested to transform a unit square based on the image given to you, and then undergo the transformations matrix P. How would the image look like in this case, right? Okay, so let me show it to you how it look like. So here, basically we have, before we start, here we have the origin. We have the coordinate A, which is 1, 0, coordinate B, which is 0, 1, and C is a 1, 1. And then these four vertices will form the unit square shape, okay, two-dimensional shape. Okay. Now, just to explain a bit, this 1, 0 basically means um, the original coordinate 1, 0. Okay, just let me write it down first before you look at what happened. Now, the structure of this basically mean the first column, hold on, the first column 1, 0 now actually refer to transforming the this coordinate here 1, 0 to 1, 0. Okay, so the 1, 0 basically mean when this coordinate A at 1, 0 is transformed under this matrix P, the image will still remain as 1, 0, which means there's no change in the image. You can see that this 1, 0 is the same as the coordinate A itself. Right? Now, usually the main focus here is just A and B. Okay. Now, as for B will undergo transformations. So under uh, B here, the original coordinate for B is 0, 1. Okay. Now, when undergo transformations P, what happens is that this coordinate here or this object here will be transformed to phi 1. Now, that is what it actually means here. So this is coordinate A and then transform to A prime, which is its image. This is coordinate B, transform to B prime. Okay, so basically that's how it look like. Now let me show you the effect in this case. Right? Okay. Now, other than that, before I show you, you can also work out like what will happen to the origin. What will happen to the object origin undergo these transformations. Now that is very straightforward. All you need to do is just take this 1501. If you wish to know what is the image for the object 00, so you just need to write down 00 here. It will be transformed to 00. If you just carry out the matrix operation here, it will be translated to 00, which means the origin remain at the same location. And then if you're interested to know what happened to this position here, 1, 1. Now the same thing, you can carry out the same operations like 1, 1. Here you are saying that I want to transform this object 1, 1, and then I want to find out where this object will be transformed to. So it will be transformed to, you can see that that will be a 6 and 1. Okay, now by putting all these coordinate into its plane here, we'll see what sorts of transformations are we looking at. Okay, now let me show it to you how it look like. Oops, this one keep on. Okay, just let me run the mesh here. Okay, all right. Now let's try to map all these coordinate onto the point that we have calculated just now. Okay, you can see that. So B will be will be transformed to that position of phi 1. You can see that. B is transformed to phi 1. And then C is transformed to 6 1 according to our calculation. And then A will still remain at its same position. Now you can see that the effect of this transformation matrix is a shear. First of all, you have to recognize that the name for this transformation effect, is called shear. And then you will notice that there is no change to the coordinate that is lying on the x-axis. So we'll say that this is a shear fixed x-axis, and then with a shear factor of. Okay, now how do you find the shear factor? Shear factor is quite simple here. Now all you need to do is just find out. Now take for instance, it, it would be this particular width, for instance. So for this image here, B, you can look at this image here. All you need to do is just draw a triangle here. You can see this triangle. Okay, now the shear factor is given by the width of this triangle, which is 1, 2, 3, 4, 5, 5 unit, over the height, which is 1 unit. So the shear factor of 5. Actually, we can recognize this shear factor quite easily from the structure of the matrix system. Therefore, we have successfully described this transformation matrix. This transformation P is a shear fixed x-axis with a factor of 5 here. Right. Now I hope that is clear for the first question. All right, let's take a look at the second part of this question here. Involve another transformation matrix Q. Here we are informed that transformations matrix Q is a stretch parallel to the y-axis with a scale factor of 4. A scale factor of 4. So how do we represent this matrix transformations Q here? Okay, now just let me show you how the effect of this transformation matrix look like. Then later we can decide on the structure of this matrix. I think that is the second one. Yep, I think I messed up. Let me rerun that. It's supposed to be matrix 2 here. Yep. Okay. Now you can see that it's a stretch parallel to the y-axis with a scale factor 4, which means the shape will be extended 4 unit long. Yep, that is how the stretch would look like eventually. So you can see that the B has been stretched to a new position, B prime, but the A will still remain at the same position. The C would have been stretched to a new position, C prime there. Okay, now that will be our transformations Q. So how are we going to write this? Very simple. Again, you need to focus on the position A and position B first. So let's start from A. For that, our object A, we have positions of 1, 0. Okay, now we know that under these transformations Q, the A would be mapped to A also. So there's no change to A, which is A prime. Whereby B, okay, we look at B here. B originally was 0, 1, and then undergo transformations of Q. This B would have been stretched to a new position here, which is 0, 4. Now that will be our new image for B here. Okay. Now, once we have obtained this, we can straight away finalize the transformations Q. Therefore, we can conclude that Q can be represented as, all you need to do is just copy this one down, 1, 0, this result here, and 0, 4. Okay, now this is a stretch parallel to y-axis with a stretch factor of 4. You can recognize that the factor 4 is here. Right, so I hope that is clear. If you want to check whether this matrix is correct, just for checking purpose, now based on these simulations, we know that C would have been stretched to this position, so we can check if we use this matrix and then transform this object here, which is 1, 1, will I be able to obtain the new image C prime here? Okay, let's look at that. We will have a 1 and then we'll have a 4. So let's check that is 1, 4. Yes. So this is the correct transformation matrix that represent a stretch parallel to y-axis with a scale factor of 4 there. Right, now I hope that is clear. We're going to look at the next section shortly. Right, our third sections for this question here. Now transformation matrix T is different transformations that consists of combinations of transformations P followed by transformations Q. Now we are going to discover the transformation matrix for T here. Okay. Now to do that, this is quite direct. It is mentioned that the T is given by transformations P followed by Q. So transformations P followed by Q. Now the convention is we have to start from P first, okay, and then followed by Q. Okay. Now therefore the correct order would be we're going to write Q first, then followed by P here. I know that is a bit confusing. Usually we read from left to right, but for transformation matrix, it's best to read it from right to left. So we're going to perform P first, followed by Q here. Okay. Now, once you get the sequence or the order correct, then all we need to do is just substitute our matrix Q, now which we have obtained just now, is 1, 0, 0, 4. I hope that you still remember. And then transformation matrix P is given here, which is 1, 5, 0, 1 here. Okay, all we need to do is just complete this matrix operation. So we have, let me see, we have 1, okay, that will be a 5, and then here we have a 0, and then finally we have 4 here. Right, now this is the matrix T that represent the combinations of transformations matrix P and Q. Okay, now let me show you how the effect would actually look like. Okay, now just let me show you the effect here. Okay, hopefully it will work in this case. Okay. Okay, let's look at the transformation matrix. So first of all, we go through the shear. That is transformation matrix P. Okay. And then thereafter, we're going to go through transformations matrix Q, which is a stretch parallel to y-axis. Now that is a stretch factor of 4. So therefore, that will be our final image that undergo the transformation matrix T here. Okay, now I hope that is clear. Now we're going to move on to the last sections to this question. All right, so the last sections to this question here, we have seen that the unit square object, undergo transformations matrix T. This is how it look like. Just let me show it to you one more time. So first of all, you undergo a shear with a shear factor of 5 unit, with the x-axis fixed, and then thereafter it undergo a parallel stretch along the y-axis. Now that will be our image. They undergo transformation matrix T here. Okay, all right. Now there you have it. Now there's an easy way to obtain the area of the image of this unit square undergo transformation matrix. So this is the area that we are interested to get, the one that has been stretched. Okay, now let's take a look at how to obtain this using geometrical approach based on this drawing here. Therefore, the area of this image, so I just make it short here, of this image that undergo the transformation matrix T. Okay, now we can, I'm going to label this as um, area, let me see, how do I call this? Area AT then. Okay, easier to remember. So this area AT can be given as quite easy. So the easier way is to basically just take the area of the rectangle and then subtract off with these two triangle there. So therefore, I'm actually getting 4 by 6, which is the area of the rectangle, and then I need to remove out this triangle here, which is given by a 4 and 5. Okay, and then I need to remove off the other triangle, which is given by 4 and 5 also, which is actually the same area. So therefore you can simplify that as 4 by 6 by 4 by 5 actually. And then that is typically just 4 unit square. Now that will be the area of the image of the unit square that undergo the transformation matrix T there, 4 unit square. And then we are done. Okay, now there's another way to obtain this area, okay, without using geometry. If you can't visualize, if you don't have time to draw it out, okay, how can we make use of that transformation matrix T that we had developed just now? I'm going to write down one more time. That is actually 1504 that we have developed previously. How are we going to make use of this? Okay, now first of all, the first step would be we can make use of its determinant. So let's work out the determinant for t. Determinant for t is basically, I'm going to label this. This is a, b, oops, this is d, b, c. Okay, it doesn't matter which one come first, but basically the determinant in this case is ad minus bc here. Okay, now that will be a 4 minus a 0, which is actually a 4 unit here. Okay, now there's one more thing about determinant. Usually we put a absolute sign here, so just in case we forgot about this, whenever you apply determinant, okay, we always put a absolute sign across this expression. So therefore this is 4. What does this 4 actually represent in terms of its geometrical effect? So the determinant equal to 4 basically means that the unit square image has undergo an enlargement of 4 units actually. Enlargement of 4 units. So therefore, we can use this general formula. Area of object, the original object before you undergo transformations will be the same as the determinant. Okay, maybe I can rewrite using this symbol here. So just put a modulus sign across a T to represent determinant. Multiply by, oops, I think I write it down wrongly. Supposed to be area of image. Yeah, area of image equal to the determinant multiplied by area of object. So the area of object that we are referring to is this object here, the unit square. So you can see that this is actually 4 unit by 1 unit square. That would actually give us a 4 unit square, which is exactly the same answer that we have obtained here. Right. So there are two approaches you can use. You can either draw out the image and then work out the area itself. Here is quite easy because the coordinate is quite small. What if they give you some coordinates that is larger, or maybe it's in a three-dimensional space? So therefore, it's very hard for us to visualize and then see the geometry itself, right? So it's always best we have another tool to work with the area of the image. Okay, now I hope that this has been informative. Don't forget, uh, if you like what you're looking at, don't forget to subscribe and then press the notifications bell. Okay, so that you can receive the latest video there. Right, thank you very much for watching. Until I see you again, take care, everyone.